All right, I think I'm gonna get started now. So thank you all for coming and welcome. Name of my talk is Real World Tips, Tricks, and Notes of Using epoll-based busy polling to Reduce Latency. I'm going to be moving around a lot as I speak because I'm freezing cold in this room, so apologies in advance. So just to get it started, hi, my name is Joe. I work at Fastly, and my opinions are my own. This is what a computer at Fastly looks like. It is a computer that runs lots of different services, lots of different daemons. We have like a web server that runs, which we use H2O. I'll talk a little bit about the web server aspect of this later, but the point of this diagram is just to give you the idea that like system-wide settings don't necessarily work for us because we run so many different daemons. And certain things are latency sensitive and other things are not so much. And that's sort of like a core feature of what I'm going to be talking about today is like making things work a particular way for certain apps, but not other apps. So if you fall asleep for the rest of the talk, the overall takeaways, the only part that you really need to care about is the slide, which is that in our measurements, which I'm going to show like toward the end, some graphs, overall, BusyPoll helped us reduce latency in production workloads. We needed some tweaks to get us there, and I'm going to take you through what some of those tweaks are with like some pseudocode and stuff like that. The system-wide configs that existed when I first started experimenting with this were like way too coarse-grained. So I'm going to like show you a little bit about what I did to overcome some of that. There's more work to be done in the kernel, and I'm going to try to both suggest things that if there's any driver maintainers in the room, like things you all might be able to do. I'm going to talk about some things that I hope to do, and then some things that like Fastly, the company that I work for, hopes to do. And in general, more documentation about how different things in the networking stack work, like overall, would be really, really useful. And I have something about that toward the end as well. So before we can talk about busy polling, I'm going to talk to you a little bit about NAPI. I'm just going to start with a very high level diagram. Like we don't need to go into like all of the specific details about NAPI, but I just want to introduce this so that I can better explain at least my understanding of how busy poll works a little bit later. So simple diagram, this is your computer. It looks exactly like this. You have a network card with hardware queues and you have a CPU. Data arrives. An interrupt is generated. This kicks off the kernel, and the kernel begins running softirq to then harvest packets from the device. And so as additional packets are arriving while softirq is running, you're not generating additional interrupts. That's just like very high level, like my understanding of like how the whole NAPI process works, right? Like data arrival comes, an interrupt is generated, NAPI is kicked off, softirq runs, interrupts are disabled, data is harvested. That's like the basic thing of like how NAPI works. And so if I were to try to summarize it, from my understanding is like NAPI reduces interrupt load, can presumably improve CPU cache efficiency. And in my opinion, and this is just conjecture, is that it should benefit high-speed NICs because higher speed NICs mean you have faster data arrival, which would mean more interrupts are generated. But real-world data from a production machine that we have with lots of traffic suggests something slightly different, which was surprising to me when I looked at the data. This is just a graph of how CPU time is spent on a machine at Fastly during like a high traffic event. And that orange band at the very top, that's actually measuring busy IRQ time. And that amounts for about 10 to 15% of the CPU. And I was actually really confused by this the first time I saw it, because in my mind, I thought like, okay, if NAPI is going to do its thing, I would expect like interrupt load to get to a point and then like level off, because then softirq would just be running and you wouldn't be getting additional interrupt load. But what I was seeing on this particular machine was that the interrupt load was so high that it was actually reducing our instructions per cycle. And so we were sort of like tripping over ourselves and not able to make forward progress, spending a lot of CPU in order to be in that state where we're not able to make forward progress. And so I thought that was pretty interesting. And this just felt like there was something wrong with the configuration to me. It just felt like there was this huge amount of IRQ traffic. I didn't even know if it was network IRQs or not. I just was like, okay, we're just a lot of IRQ traffic. Could be anything. Could be disks for all I know. Could be some other random thing. Who knows? But it was just a huge amount of IRQ traffic. So somebody that I work closely with came up with this idea, which was let's try to graph NAPI efficiency. And what I mean by this is the number of received packets per interrupt. And I should mention that for the two network cards that we use at Fastly, we use primarily either Intel i40E devices or Mellanox 5 NICs. And in both of those cases, interrupts are multiplexed. So you have one IRQ that's used for both transmit completions and for receive. So there's not really an easy way to disambiguate like what the purpose of the IRQ is unless you do a bunch of driver hacking. But anyway, the point of this graph is just to show that like when we're under load, we're generating an interrupt and we're only servicing like 0.5 receive packets per interrupt, which to me felt like there was something really wrong with our configuration. Like it felt like we were totally interrupt driven and like NAPI wasn't doing its job. And so like the first thing I turned to try to figure out why, like to try to figure out how to fix this, like I wanted to make the system more NAPI efficient to reduce the interrupt load. And so the first thing I tried was like, okay, well, what if I try reducing the number of receive queues, because then more packets will go to fewer queues. So presumably NAPI will be able to harvest more packets every time it runs. And I can configure IRQ coalescing. Like I don't need that many like transmit completions to be generated. What if I try and experiment doing that? So I tried that, and I tried the simplest thing you could possibly try. This graph on the right, I like modified the i40E driver, count hardware IRQ events, and then report them to a dashboard so I could try this just like in a test lab to see if this worked. And so on the top graph is just showing like the IRQ count rates. And then you can see where I adjust the TXU seconds IRQ coalescing parameter using ethtool. And I chose a number, 312 microseconds. Why 312? The answer to that question is because the i40E NICs do 25 gigabits, and you can do math, and you can figure out how many nanoseconds you're allowed before you are no longer able to maintain the line rate. I chose a number that was like below, like I could have chosen a larger number, but I chose 312. And I can show that like the IRQ generation count like dropped significantly, but iPerf3 was still showing that our transmit rate, our total throughput was unaffected. So I thought that was interesting, and I was like, okay, let me try like running this like on a machine like in production and get some actual data on i40E and Mellanox 5 if we play with like IRQ coalescing. And so I did that. You don't have to worry about the numbers. Like the slides will be online later. You can download it and look at the numbers if you want. The TLDR is that like there was a large reduction in what I'm calling like no work. And what I mean by that is non-receive work IRQs on i40E, like maybe about 15% or so of a reduction of IRQs, which is pretty substantial. Like I thought that was pretty dope. On Mellanox 5, we only got about 3 to 5% improvement, which I think is kind of expected. Like the Mellanox 5 NICs are a lot faster. They're 100 gigabits, so they're generating a lot more IRQs. And so maybe I wouldn't get as much by, I can't push the TX coalescing parameter out as far, and so only maybe lower it like a little bit. And I got like a 3 to 5% improvement when I did that, and I was like, okay, that's cool. So that was a tiny improvement, but I still felt like there was something I was missing. And so I spent a lot of time reading kernel code to see like what other options existed that were out there that maybe I didn't know about or that I could take advantage of. And I stumbled on these two things in the kernel, NAPI defer hard IRQs and grow flush timeout. And it took me a little bit to understand like how these work, but the way that I think about it, and feel free to correct me if I'm wrong, but the way that I think about this is I imagine this as like a method of software IRQ coalescing. You can basically, this is like a system-wide setting that you can set to say like there's some code in a function called NAPI complete done that will tell the driver like if it should or should not re-enable interrupts from the device, and you can affect whether or not the driver will do this by setting these values, and you can process incoming network data using a timer instead of a hardware interrupt. And so the idea is basically that you can defer the re-enablement of IRQs from the device and then fire a timer at whatever rate you want instead. And so I thought this was interesting, and I was like, okay, well, maybe I can play with these numbers and I can see if at least the busy IRQ time that we're spending is actually network receive packets, like network IRQs or not. Because that's still at this point, I didn't really know. I just knew that like I could reduce IRQs a little bit by pushing TX coalescing out, but I didn't know for sure that this was network based. So I tried setting some like random values that I guessed. This graph is kind of hard to see, but what you can see on the top graph, this is CPU usage, and that like orange band at the top is the amount of time we spend with IRQ, and you can see that there's like a huge byte gets taken out of it, and it drops pretty significantly. This is like as soon as I set those two settings, and it didn't seem to affect throughput a whole lot, but it does reduce our CPU usage considerably under load. I thought that was really interesting. And so the takeaway was like using these settings reduced CPU usage considerably, which to me proved one important fact, which was just that like receive interrupts are a significant source of CPU use for us with our configuration on that machine. But there's a pretty big caveat to doing that. And this is that when you do this, you're obviously going to introduce latency, right? Because like you're going to set the timer to some value where it's going to fire less often than your interrupts are firing. And so you're going to induce latency. And like maybe that's okay for your app, or maybe it's not. I don't know. For us, it would be okay for some apps, but not okay for other apps. And so this led to more kernel code reading. And I was like, okay, this is kind of interesting. Like I found like a new thing I learned about. I want to see like what else is out there that I don't know about that I can use. And then I stumbled on something that I was really confused about. I stumbled on this thing, SO incoming NAPI ID. I saw this like mentions of this in the kernel. I was just like, what is this thing? I have no idea what this does. I spent a bunch of time Googling it. I had like no clue what this thing was for. And I stumbled on an email from somebody named Kong Wang in 2019 who also didn't know what it did. This is the email to the public mailing list. And it's like, it says from Kong Wang, look at number 3 on the bottom, highlighted in orange. It says, how is SO incoming NAPI ID supposed to be used? I can't find any useful documents online, any example or more detailed doc. And here's the thing, like at Fastly, I work on lots of stuff, not just the kernel. Like I'm not a kernel developer. I just do some upstream kernel work, but I also do userland stuff. I do stuff like all over the place. So I had no idea, like I didn't know that Kong Wang wrote kernel code. Like I saw this email and I was like, okay, this person doesn't know the same thing I don't know. Like I was like, I wonder if they work on kernel stuff. And so like it turns out that Kong Wang writes kernel code, which is maybe not surprising to you all, but like I didn't know that because I'm not a kernel developer. And I was like, and so you know, like if you go to GitWeb and you're looking at netnext, you can like type in a person's name and see how much kernel code they wrote. And so I had seen a bunch of emails from Kong Wang in the mailing list. I think he rejected one of my patches or something at the time. And I was like, let me just see like how much kernel code this person has written. Because I was thinking like, okay, they don't know what it is. I don't know what it is. Like, you know, we agree on this one thing that we don't understand what this thing does. And so I looked at like Kong Wang's like GitWeb history, and I was like, wow, this person, like, I was like, this person writes like an absolutely tremendous amount of kernel code. So if Kong Wang has no idea what this thing does, then I feel a lot less bad about also not knowing what this thing does. So you know, it's like, you know, actually like he writes a huge amount of kernel code, and if they don't know what it does, then you know, it's really not surprising that I had no idea what it did either. There is a little bit of documentation about it in the man page if you read the socket man page. This documentation helped me understand a little bit more about what this is supposed to do. The key thing here that I took away from this, and you can like read this whole blurb like later if you download the slides, but what I took away from reading this is essentially that like this is an ID you can use to map an application thread to a hardware NIC queue to streamline the flow of data from the NIC to the application. That's like the last line of this man page. And that was interesting. And I was like thinking about this for a while, and I was like, okay, this like vaguely seems like flow steering to me. I still didn't totally understand exactly like how you would use it or what other interactions there would be. And there are some which I'm going to get into shortly. But I stumbled on a pull request that was open against memcached that adds support for this thing. I'm not going to read you the pull request, commit message, but you can click on the link later and check it out. And I'm going to explain how you might use SO incoming NAPI ID or how specifically memcached uses it. So remember this whole diagram I showed you before, just like it's a vague high level diagram about NAPI. So if you just like, there's like one thing I left out of this, which is that in the hardware queues on your network card, each of these things has a system-wide unique ID, which is called the NAPI ID. So just remember that. And the example pseudocode usage of how you might use SO incoming NAPI ID, like this is just like code I typed for the slide. It probably doesn't actually compile. So like just as a disclaimer, but you'd have your one thread that does accept. You'd accept the connection. You'd use get sock opt and ask, hey, which NAPI ID did this file descriptor come in on? And now dispatch to one of my worker threads this file descriptor based on the NAPI ID that I got. And so in diagram form, just because I think it's easier to understand if you diagram it, if you imagine like all of the NAPI things in the kernel happening in the gray box, you have your user program in this orange box, and the user program has a single thread doing accept, and it has like some code dispatching based on NAPI ID, like I showed you in the previous slide, to the worker threads. And so essentially what you're doing is you're saying like Nick received queue number 1 is going to get dispatched always to thread number 1, and like Nick received queue 4 is going to get dispatched always to thread number 4. That's like a way of using it. And there's also a really interesting modification involving epoll, which I'm going to get to in a moment. But this is like one way you could use SO incoming NAPI ID. And so I think my understanding from the man page and from looking at the code in memcached is that SO incoming NAPI ID is a way of determining which QID is associated with the connection. And then your application can select which worker thread based on the QID should handle that connection. And it allows you, like the man page says, to map apps to NIC hardware queues and threads. And I presume this should improve like cache hit rates and memory locality. And I was like still going down this rabbit hole. And there's a little more though. There's something really interesting that's tied into this, which took me like a little bit longer to understand how it worked. Before I can tell you about like this really interesting NAPI ID and like busy poll thing, I first want to just very, very briefly at a super high level show you how epoll wait and NAPI work normally so that you can understand how it works when you use it in busy poll mode. So how it works normally, let's just like assume this is on the same CPU. In kernel is yellow, in userland is orange, and you have your app, and maybe your app is a web server or something, I don't know. You have your file descriptors. Maybe your file descriptors are client connections, like people on the internet trying to talk to you, your web app. And in the kernel, like data is arriving. NAPI is running asynchronously. Like data is arriving, IRQs are firing. NAPI is doing its thing. It's like running the network stack, pushing packets like up into file descriptors. And then in userland, your app occasionally has the opportunity to call epoll wait and ask the kernel, hey, which file descriptors are ready? Epoll wait is going to go and like do its thing and figure out like, okay, whatever, these file descriptors are ready. And it's going to tell your app, hey, like there's some file descriptors that are ready. Right. And so like the key takeaway from this is just that like NAPI and all the network processing is getting triggered asynchronously by interrupts coming in. And then your app is occasionally asking like, hey, what's ready for me to process? That's like how what I would describe normal epoll wait works, but there is an epoll specific modification that was added to the kernel for SO incoming NAPI ID. The SO incoming NAPI ID of the last file descriptor added to an epoll set can be busy polled. And do so, you'd want to ensure that all file descriptors that are added to the epoll set are from the same receive queue, because it's the last one in wins, basically. Right? So if you were to add file descriptors from different receive queues to the same epoll set, the NAPI ID associated with that epoll set will just be whatever the last file descriptor added was. So so that would mean that would be the thing that would get busy polled. So the other ones wouldn't. But you'd want to ensure that all file descriptors getting added come from the same receive queue to make this work properly. So you need to do that, and you need to set the system-wide setting, the system-wide $60 proc value in busy poll. And if you do that, it kind of looks like this. I'm going to show you another diagram similar to the last one, right? So you got like kernel in yellow, userland in orange. You got your app and your file descriptors like last time. Your app now calls epoll wait and asks, hey, which file descriptors are ready? Epoll wait can now like synchronously call the driver's NAPI poll function and actually trigger the network stack to run, which I think is really interesting actually, like because now instead of CPU time being accounted as like soft IRQ time, you're actually running the networking stack as a result of a system call. So it's like now in system time, which I think is kind of interesting difference. And then like, NAPI poll does its thing, the network stack runs, data ends up in file descriptors, and then epoll wait will return and say, hey, there's a bunch of ready file descriptors. So I thought this was pretty interesting. Like this seemed like a way to change the way you're processing network data. And it seemed like there could be some advantages to doing this. I would summarize this as like if you use epoll with SO incoming NAPI ID, with like the system-wide busy poll thing set, all file descriptors must have the same NAPI ID. Epoll weight drives packet processing. Now, probably you'd get better cache efficiency. And the app can decide when to do network processing versus its own work. And so what I mean by that, and this is modulo, like interrupts still coming in, which I'm going to get to in a second, but like in general, the way I kept thinking about this was like, okay, like you have your web app and like maybe you're doing TLS or maybe you're doing like, I don't know, compression or something. And instead of like in the middle of doing compression or in the middle of doing crypto, getting an interrupt and then suddenly like kernel runs and then, your app runs again later and tries to pick up. What if like you could just finish doing the TLS that you have already and then tell the kernel like, hey, like my userland program is now done and like I'm ready for new data to do TLS on. I'm ready for new data to do compression on, instead of being constantly interrupted like while you're doing stuff. So I thought like, okay, that's like a pretty interesting thing, but this is modulo, like this is limited by like device IRQs, which can still fire. And I'm going to show you a flame graph about this like a little bit later, which is, I think, but the biggest problem is that this is system wide. So if you turn on that sysctl, suddenly everything on your computer starts busy polling. And this kind of sucks because, just as an example, like we run a lot of Golang telemetry daemons, and a lot of Golang telemetry, like I think like internally in Golang, they use epoll a lot. And so like our telemetry daemons started using like 100% CPU usage all over the place. And like those are not, so those are A, not set up to do busy polling, and B, they're not necessarily latency sensitive in the same way that a web server is, or a web app server is. And so, that was kind of like a non-starter for us. Like there's just like no way we could use this thing because suddenly like all these random things on our system just started using 100% CPU. And I was like, okay, this is not what we want. So I wrote a patch to make busy poll, epoll context specific via an ioctl. And you can click on the link and read the patch. This is cover letter. Cover letter explains a lot about like motivation and like how you might use it and so on and so forth. And I took the time to thread this through to glibc, UC libc, ng, and I sent a patch to muzzle. I don't know if that's how you pronounce it or not, but that's it. I sent a patch to muzzle. Hasn't been merged yet. I have no idea if it ever will be. But this is in glibc. So like this ioctl interface should be easy to use for userland apps. When glibc makes a new version and you get it in your Linux distribution in like 10 years or whatever. And because I was complaining about documentation, part of that falls on me as somebody who works on this or who was working on this. I added a man page, which was added to the man pages project. I have no idea how often distributions pull these in, but there's a man page that explains how to use the ioctl, explains what the parameters are, what you set them to, and so on. Around the same time that I was like researching this internally at Fastly and like playing around with it, an academic paper was published, and I had no idea that like this work was also being looked at by some folks in a university. And this paper is really, really interesting. So again, like if you download the slides later, you can click on the link and read the full paper. The title of the paper is Kernel versus User Level Networking, Don't Throw Out the Stack with the Interrupts. Very provocative title. It was super interesting. The paper goes through lots of different methods of trying to improve instructions per cycle, essentially. And they talk about things like, using their terminology, they talk about like IRQ packing and IRQ suppression. And you can read the paper to learn more about like what they mean by that specifically. But in the paper, they talk about SO incoming NAPI ID, and they run a test on memcache, which supports SO incoming NAPI ID. And they included in their paper a small kernel patch that changes the way interrupts are handled. And they were able to measure a really surprising number. They measured that like kernel busy polling outperforms a vanilla configuration by at least 30%. And so this was really interesting to me because like I was hacking on this busy polling thing and I was like, I don't know if this is going to go anywhere or not. And then this paper came out and they said they got these crazy numbers and I was like, wow, 30%. Like I want 30%. How do I get 30%? And so the paper was showing promising results, but would I see those same results in our production workloads? Well, the only way to answer that question would be to try actually using SO incoming NAPI ID, and adding support for that to our app was much, much trickier than I expected. And I'm going to explain to you what we did. There's probably a lot of different ways to solve this problem, but I'm going to tell you about what we did. Okay, so at Fastly, just to give you some background on like before I explain to you like what I ended up actually doing. So at Fastly, we use an open source web server called H2O, and H2O uses SO reuse port that all of the worker threads can listen on the same port, and the kernel can delegate incoming connections to the proper file descriptors as it deems necessary, and you can control that with like a BPF program. Our machines generally have 1 or 2 dual port NICs, meaning that we either have 2 or 4 Ethernet interfaces. And we run one process that listens on everything. It listens on all NICs, on all ports, on all NICs. And we listen on lots of ports. For the purposes of like today's conversation, we could just assume it's port 80 and port 443 for H1 and H2. And generally speaking, we use Mellanox Connect X5EX NICs. We do have a bunch of Intel NICs, but I'm going to focus mostly on the Mellanox stuff because that's like what we're using for the most part. And moving forward, we're going to use more Mellanox 5 NICs. A rough diagram of what this looks like, if you were to try to draw what the system looks like today when you run H2O, you can see like on the top, there are your H2O worker threads that are doing like HTTP. And they're listening on ports 80 and 443. And when they use SO reuse port, really what you're doing in the kernel is you're creating reuse port groups that are what I'm going to say delimited or like, separated via the port number, right? And so like all of these threads have file descriptors that are associated and with port 80. And so like this forms the reuse port group in the kernel. And then these threads all have, are all file descriptors that are listening on port 443, and that also forms a reuse port group. And connections can come in from any one of 4 network interfaces, to any of these ports, and then they all get distributed by the kernel to the worker threads. That's like the rough diagram of like how the system worked before. And what I was trying to do is change the system from working like this to working differently. And I was like, I saw this and I was like, okay, I know what to do. And maybe a lot of you were thinking this too. You're like, I know what to do. This is really easy, right? Like step 1, create a custom RSX context. Here flows to CPUs where web server worker threads run. That's pretty easy. Okay, I can do that. Push RQs out as far as I can because I'm going to do busy polling. So like I don't actually really need byte interrupts anymore. So I can do that. We'll just insert a really simple reuse port BPF filter into the web server code to distribute connections to threads. Easy. And then I can just enable busy poll just for the web server with an ioctl. And like how hard could that possibly be, right? So I'm going to include in the slides just like a screenshot of like what an ethtool script might look like to set this up. And the reason why I'm doing this is because it took me a while to figure out like the right command line incantations. I'm not going to like read through every single line. I just want this to be like documented so that if anybody like stumbles on this in the future, like you'll be able to figure it out. But basically what I ended up doing, like the summary of this whole thing, which you can't read because it's probably too small, is simply that I'm creating a custom RSX context that reserves a set of hardware queues on the NIC, typically for ports 80 and 443. And then everything else, like all the administrative stuff, like let's say like SSH or whatever, all goes to a separate set of queues, right? And the idea here is we create one custom RSX context, which reserves a set of queues just for the traffic we care about, like traffic on port 80 and 443. And we use, you can see like sort of at the top here, it's kind of hard to see, but sort of partway down, I'm using a feature that was added by the Mellanox 5 folks. So thanks a lot to the Mellanox folks for doing this. This is per queue coalescing. So basically saying like for the queues that I'm going to busy poll on, I'm going to push out interrupt rates as far as I can, supported by hardware, which turns out to be these values here. But for the other queues that I'm not doing busy polling on, that are just like other apps that are not ready for this, like they're just going to have the default settings. And so being able to set things on a per queue basis was like very, very important for this like prototype that I ended up building. And so that takes care of the first 2 things on the list, right? Like I create a custom RSX context, push IRQs out using ethtool. That's pretty easy. So now I just need to insert this BPF filter and use ioctl. There's this BPF filter floating around on the internet. I think this is from a pull request or a patch that was posted to a mailing list for Nginx. And that's like where I found this originally. And this BPF code is really, really simple, and it is deceivingly simple. So what you can see from this is just saying like, this is just taking like the queue mapping of the SKB, and then it's doing that queue mapping, which can be a number from 0 up to the number of queues, hardware queues on the device, and it's doing that modulo n. Presumably n in this case would be the number of threads you have. And so the idea is that like this reuse port BPF program would look at the queue mapping and then decide based on the queue mapping, modulo the number of threads, which thread would get a particular connection. And you would think that if you did this, right, all connections coming in on the same queue mapping would end up at the same thread, and that would maintain the invariant I told you about earlier, which is that all file descriptors added to an epoll context have to have the same NAPI ID. So this is the first thing I tried. It turns out this doesn't actually work when you have multiple NICs, and I'm going to show you a buggy example to explain why this doesn't work. So imagine you have your worker threads at the top and you have your reuse port CBPF program installed. You're just doing queue mapping modulo thread count. And so a connection comes in and let's say it's, hardware queue number 3 on NIC 0. Let's say that thing has NAPI ID 1439, right? So 3 modulo 4 is 3. So then, the kernel distributes this to file descriptor number 3 in the set, and then that wakes up worker thread number 3, and then worker thread number 3 adds that file descriptor to its epoll set. Everything is fine so far, right? Like this file descriptor has been added just fine to worker thread number 3, and its epoll set now has NAPI ID 1439. Everything is good to go. Then you get another connection. This is queue number 3, but on NIC 1. This is a different hardware receive queue, and this has NAPI ID 1443, which is different than the NAPI ID on the last slide. But in this case, you're still doing the same thing. You're doing the receive queue, so Q3, modulo the number of threads, 4, and 3 mod 4 is 3. So you're still selecting file descriptor number 3, and now you've sent 2 file descriptors that came in on different hardware queues, the same thread, which breaks invariant you need to have if you want busy polling to work properly. So I said like this isn't strictly true, but like on this slide I'm saying thread 3 has been given 2 connections with different NAPI IDs. That part is true. This next part's not strictly true, which is what I'm saying is that this breaks busy polling is not allowed. You could do it if you want. The last thing you add is the only thing that's going to get busy polled though. So that's probably not what you actually want. And so that's why I'm saying it breaks busy poll and probably is not what you actually wanted. So how to fix this? A few ways come to mind, but this is what I did. I spent a huge amount of time reading kernel code. And I stumbled on this piece of code in the kernel in reuse port add sock. So when you're adding a file descriptor to a reuse port group, there's this check that occurs to say like, hey, is this thing bound same if index? And so I started thinking like, I wonder if I can delimit reuse port groups, not just by their port number, but also the if index of the device. And so like, what if listen sockets were grouped per NIC with SO bind to device? And so in effect, what I'm trying to do is turn this diagram from earlier to look a little bit more like this, where the reuse port groups exist for port 80, as you can see there. Yeah, so when you're looking at it on the left side, on the top, you have reuse port group 1, so port 80. If that reuse port would only distribute connections coming in on NIC 1, and if I had another reuse port group for NIC 2 for port 80, and if I can delimit things based on the NIC index, then that CBPF program that I showed you before would run and actually work, because now that CBPF program is only being run essentially on like a per NIC basis. You can think about it like that. And it turns out the code to actually doing this is fairly reasonable. Here is just really, really rough pseudocode of how I approach this. This is not real code. This is code I typed into Vim and screenshotted to put in this slide. There is no way this actually like will compile. This should give you an example of like the way that I thought about doing this, which was like, you have your 2 network interfaces, ETH0, ETH1. You're iterating through those interfaces, and then per interface, you're creating all of your listen sockets, and you're calling SO bind to device to bind those listen sockets to the device that you're currently on in the outer for loop. And after you do bind to device, you call SO reuse port to turn on reuse port. And then if it's the first photo descriptor in the set, then just apply the BPF filter that I was showing you before. And that's pretty much what I did. Like I just created the sockets, called reuse port, applied the BPF filter, and then after you do all that at the very end, then you can call listen on all of them so that connections start getting distributed and they end up in the right place. And it turns out this actually worked, surprisingly. Like I didn't think it was going to work, but it did. And now incoming connections are going to worker threads while maintaining the constraint that each thread maps only to one NAPI ID. So this was solving the problem that I was having initially. And I ended up, with a system that looks like this, which allowed me then to do busy polling. And before I talk about like the results and busy polling and stuff, I just want to briefly mention what our accept path looks like, because I think that might also be interesting for folks as well. Like you could do, okay, you can do whatever you want. I'm going to tell you what I did though. So what I did for the accept path is our app has configuration that gets loaded at app start time. And the config basically shows you Ethernet devices, like the config basically outlines like, here are the Ethernet devices and here are the CPUs that are pneumolocal to them. And the app reads this in when it starts up and it builds up a map internally. And then the accept path kind of looks like this in pseudocode where like a request comes in, a thread, a file descriptor on a thread is like active. That thread then wakes up and calls accept on it. And then when it calls accept, there's either two cases. Case one, the simple case is like, we've already seen connections before. And that's what the top half of this code is showing. It's just basically saying like, we've claimed a CPU and this thread has also claimed a NAPI ID. And I just have a check, like a safety check sort of at the bottom, just right above the else case, you can see that, where it's like, if for some reason we get an unexpected NAPI ID, we'd fire an alert because that would be bad and we'd want to know. And then the other case that is the slightly trickier case, which is we get a connection for the first time. This thread has never grabbed a NAPI ID before. So in our app, what we do is we use a hack that I'm going to talk about in a second, that you give the kernel an API ID and you get an Ethernet interface name back from the kernel. So we're basically, when a connection comes in, we query the kernel. We say, hey, which Ethernet device owns this API ID? The kernel responds with an Ethernet device name. Then look at the map of pneumolocal CPUs. We pull an unused CPU from that list for that NIC. And then now this thread claims that CPU and that NAPI ID. And then this thread pins itself to that CPU. So now all incoming connections are going to be pneumolocal to this worker thread that's running on a CPU that's pneumolocal to the NIC that the NAPI ID is associated with. The internal hack that I coded up for this is really bad, but there's a reason why, and I'll explain in a second. But it's kind of basically I sort of like hacked this existing ioctl, which is the ioctl for get if name. Like I think generally the way this is used, if name is used right, is like you give it an if index and then you get an interface name back. I basically like added an extra way so that you can pass in an API ID and get an interface name back. The real way to do this, or the right way, or what you should be doing instead, is using Netdev GenL. The thing is that we only use like LTS kernels at Fastly, so that doesn't exist yet in like 6.6. So there was no way for me to use Netdev GenL to solve this problem, but that would be like the right way of doing it if you have support for that. I'm gonna get to that in a bit. Okay, so anyway, I did all this stuff. What does this look like in production? What are the results? So I'll show you some graphs. So I work at a company that has a legal team, and they told me to not include the numbers. Sorry. But this graph, I'm just going to explain the X and Y axes, and I'll just like use words to tell you that the results were like meaningful. So the Y axis is the number of milliseconds of latency, and that's the Y axis. The X axis is like when the time measurement was taken. And so the really bumpy line, that's like the control system that's just doing like the standard, network processing. And the completely flat line underneath it, that's the busy pole system. And so you can see that like the busy pole system had a lot less jitter, and it was also had much better latency performance at P99. What about P39? P39s looks even better. So the yellow line across the bottom is the busy pole prototype that I was running. And the bumpy green line is just like our normal vanilla configured machine. And the difference between these two, again, like I had to clip out the actual millisecond numbers, but it's very significant. So this was like a really significant really significant improvement for us at P39s. I also grabbed P49s. I don't really like 49s. I think it's a little bit noisy, but whatever, data is data. P49s, sort of the same effect. Like the bouncy blue line is the vanilla configuration, and the sort of steadier orange line at the bottom is our busy pole prototype. And so, at least in the 3 percentile cases that I was looking at, the data looked really, really good. Right. So like the latency looks much better for the higher percentiles. But, and this is sort of where a caveat comes in, in H2O, which is our web server, we use epoll pwait2, and I'm setting the busy pole useconds to match roughly the pwait2 time. But occasionally, if busy pole comes up empty, pwait2 will run idle. Like epoll will actually has code that will deschedule itself if you're passing in a timeout. And perf measurements and flame graphs suggest that device IRQs still arrive, which kick off NAPI and induce latency. And this will be a little bit easier to understand when I show you the picture in the next graph. So this is a flame graph from a real machine. And when you call pwait2 and there's no work to do, so busy pole finishes and epoll says, okay, there's a timeout, maybe because you're running a timer wheel, let's say, userland, right? And so you're passing in a timeout to epoll. Epoll goes idle, and then while it's idle, you can kind of see part way up on the slide, I don't know, maybe 25% away up from the bottom, you can see that interrupts start to get generated. And you can see if you look up a little bit more, you can see the Mellanox 5e, NAPI poll stuff getting invoked and the networking stack happening. And so the problem with this is that now idle, when the idle process is running, you're inducing latency because now you need to wait for this soft IRQ thing to finish before epoll pwait2 is going to return and give control back to userland. And so that seems not ideal. And I was on this huge mission of okay, how do I eliminate this from happening? How can I prevent interrupts from getting generated? Even when we go idle, I had pushed the interrupt coalescing parameter out as far as was supported by hardware, just for the queues that I was busy polling, but it wasn't quite far enough, apparently. And so I started thinking, okay, well, maybe I can reduce the max events parameter to epoll pwait so that we just get less stuff every time we call epoll pwait2. And maybe we can defer IRQs even further with NAPI defer hard IRQs and grow flush timeout. So the first thing you can do, you can reduce the number of events you care about. That's pretty easy. But you can't really use the two knobs on the bottom, NAPI defer hard IRQs and grow flush timeout. At least we can't. These settings are system-wide, and other latency-sensitive apps that we run that are not yet busy pole compatible will suffer if we try to defer hard IRQs system-wide. And it also turns out that choosing the values for these two parameters is really, really hard. And what I mean by that is just imagine in your mind, your system is under load. And so in that case, you don't want interrupts to fire because you're busy polling. And so you don't need interrupts then. But when your system is not under load, you don't want to just burn CPU for no reason. I don't know, how much carbon do you want to put into Earth? It would be nice not to burn CPU for no reason. And it turns out that choosing these values is hard. And I guess you could make a program that is smart enough to adjust the values on the fly and blah, blah, blah. But I'm not smart enough to do that. That's way too hard. And that's where the future comes in. So I'm going to propose some things that you may or may not want to work on, and some things that I and Fastly am/are working on. So a thing that you all may want to work on is if you're a driver maintainer, you can add Netdev GenL support to your driver, because that allows you to map NAPI IDs back to interfaces, which is really important if you're running a busy pole app on a multi-NIC system, which I would suspect a lot of people are. This interface is already supported by a few drivers, Mellanox 4, 5, ICE, and the Broadcom BNXT. So there are examples out there on how to use this API. So if you're a driver maintainer and you're thinking maybe I should do this because Joe said so, go check out these existing code, and it could be pretty easy to figure out. In addition to that, I am currently working on a collaboration with a researcher who wrote the paper that I referenced earlier. So that paper came out, and he and I ended up emailing each other, and we started experimenting with a kernel patch which is not quite ready yet. We're still gathering data, but the kernel patch does something kind of interesting. When you are calling epoll wait and beginning your busy poll process, patch will disable interrupts during busy poll, but if busy poll comes up with no data and says like there is no data for me to harvest, then interrupts are aggressively re-enabled. And this allows you to avoid having to pick the right numbers for defer hard IRQs and grow flush timeout, which could change whether if the system is under load or idle. And in our patch, we're just using grow flush timeout as like a backstop. If things take too long, then the grow flush timer will fire and like keep everything going. We've been testing like this is a relatively small patch. It's only a couple lines of code. We've been testing it against memcache because that has support for SO incoming NAPI ID, has support for busy poll, and there are existing tests that are published by Meta or Facebook or whatever that you can run against memcache to profile it. And so we're enabling busy poll per context using like the IOCL that I added, and we're threading through this thing, and we're getting like really, really promising results, like huge reductions in tail latency in the busy poll case, which is really, really nice. And so hopefully Martin and I will be submitting an RFC with data soon to the mailing list, and hopefully you'll all be able to check that out and let us know what you think. Patch is acceptable, if the data looks good to you as well. Like we're going to try to include instructions on how to reproduce it and so on. But it's like super interesting and super promising. At least I think it is. Internally, Fastly is working on upstreaming our busy poll implementation to open source H2O. It's not quite ready yet, but we are working on it, and it will be open source. And I think this is important because if other web servers that are out there, like Nginx or something, wants to add support for busy poll, they'll be able to look at like how it's done in H2O, and they'll have like a model to follow, because we sort of had to figure this all out ourselves, get this working, or actually like I had to figure this out because I was working on this. And in the future, what I'm hoping to work on, and I don't know, maybe like Eric will disagree with me on this one, but I really want to make NAPI defer hard IRQs and grow flush timeout work per NAPI. And I think the right way maybe to do that would be via Netdev GenL. Because basically what I want to do is like already in hardware, I'm reserving a set of queues on the Mellanox 5 NIC, and I'm saying these queues push these IRQs out as far as the hardware supports. But I want to also be able to, in software, defer them even further if for some reason the hardware doesn't support it, or the hardware limits are like really low, or whatever the case may be. And so I think being able to set these two values on a per NAPI basis would be really, really helpful. So I haven't had time to even like prototype this yet because I've been so busy working on other stuff, but I'm hoping to work on this in the future. And that's it. That's the talk. Thanks for coming. Thanks for listening. I will attempt to answer questions. I don't know how much time we have or don't have, but sure. Yeah, you have a question? I don't know if we need a mic or not for the, yeah. You use this one or? Yeah, try this one.
When you enabled busy poll and got the latency numbers, the improved latency numbers, was there a trade-off somewhere in terms of CPU utilization or otherwise?
Yeah, so it was interesting. So it's a good question. The question about like, when we enable busy poll, are we using more CPU? Like what's the trade-off there? And the answer is like, yes, we're using more CPU, but our IPC is a lot better. Our instructions per cycle is a lot better. So we're actually more CPU efficient than we were with like the vanilla configuration. So like latency is reduced and we're like more CPU efficient. And so in that case, I'm happy to spend the CPU cycles if they're being spent efficiently. But yeah, that's essentially the trade-off, is like when you turn this on, you're going to burn CPU doing busy poll. Yeah.
Using more CPU because sometimes it wakes up and polls, but there's nothing actually to receive?
You're using more CPU because you're actually like, you're actively polling inside of like epoll wait. Like you're telling it like harvest data now from the NIC and run the network stack. And you're just like, doing that like every time you call epoll wait. It depends on like how you actually build your app, right? Like what sort of timeout you pass into epoll wait. The number of microseconds you set for busy poll has a parameter, which is like, how long do you want a busy poll for? So you could say like busy poll for whatever, 10 seconds. you wanted to, right? And if you did that, then like the CPU would just be consumed like in a loop calling like the driver's nap epoll function over and over and over again and potentially getting nothing.
Are you able to say like how much extra CPU utilization? Is it small, like a 10% or 20%, or is it like double?
That's a good question. I don't know off the top of my head. I would be able to say if I had recorded that and put that in the slides. I should have done that. I'm sorry I didn't. But thanks for the question.
Thank you.
Sure. It's pretty scary. A lot of questions from a lot of people who know more about computers than me. This is going to go great.
Thank you for the talk. Really enjoyed it. I have a question about latency. Another question. What did you measure? It was HTTP transaction, 4 HTTP transaction. Which kind of HTTP protocol? 1, 2, 3. What was measured in the latency? Which kind of?
Sure, that's a good question. So at Fastly in general, we support H1, H2, and H3. For the app that I was doing the prototype on, I was measuring the latency for time to first byte just for H1 and H2, and I didn't disambiguate. So I don't know, like in those graphs that I'm showing you, those graphs are just H1 and H2 time to first byte latency. Did that answer the question?
Yeah, but I will ask you after that.
Okay, sure.
One more. Yeah.
Sure, yeah.
You can go next. So do you separate driver and TCP code from your Golang bloatware, or do you run everything on like instead of CPUs?
Sorry, can you repeat the question?
Yeah, so you have a driver that's handling interrupts and traffic, then it passes SKBs to TCP stack, and then you have your user space app handling the data. It's running on the same CPUs?
Yeah. So
don't do it.
So there's a couple things I would say about that. First is that I hear what you're saying, which is like you can set aside a specific number of cores just to do like soft IRQ and network processing, and like that might work well in like certain scenarios. We've tried that and like we've benchmarked that, and actually the academic paper that I linked to tries that and benchmarks that, and there is some advantage to doing that over like the default vanilla configuration. It's just that doing BusyPoll provides an even greater benefit than just moving like interrupts around to like other. That is an option for sure. If that's like a thing that you want to do, you can totally do that. If you have enough CPUs that are pneumolocal, I suppose, to the app and the NIC, which maybe you do, maybe you don't. I don't know.
So I have a question. How do you decide when to enter back into the kernel to do epoll wait? Because I actually tried your BusyPoll based on your patch as the BusyPoll into, and the thing that I noticed is that there is too much back entering the kernel and exiting it when because BusyPolling stops in the epoll wait when you have at least one event. Basically exits the loop and comes outside. And when do you decide to re-enter? Like what if the user space is just doing work busy and the users are basically waiting in the queue?
Yeah, I mean that's like an inherent like app trade-off that you have to figure out. I suppose like the way that we tried to deal with it was just reducing the number of events we were going to allow epoll wait to harvest, and we're just like okay with calling epoll wait like more often. But your comment about like if there's just like a small number of events ready that like it exits early, that does happen, and that's the thing that I think Martin and I, he's a researcher that I've been working with, like he's noticed the same thing actually, and like this is like a thing that we're sort of playing around with too, as like maybe a future modification to like epoll-based BusyPolling. So sorry, I don't have like a great answer for you on that one, but like that is a thing that like we've measured on like other, we've seen that as well. I just try in our app, we pass in a timeout into epoll wait, so we're not returning immediately from epoll wait, and so like that maybe is an option for you. I don't know, but you might run into the same problem I'm running into, which is that like if you then go idle, then like there's opportunity for like interrupts to fire, which then induces scheduling latency. It's not necessarily that the interrupts are bad. It's just that like they fire, they trigger the network stack, and then like you don't get user land to run again as quickly or whatever.
I have a question. Did you ever hit a situation, because there's a very tight coupling between your hardware queues and your worker threads, and then the connections that get hashed to each hardware queue? Did you ever hit a situation where you ran out of user threads? There were so many connections being hashed to, because you have a limited number of queues, right? I see that in your script. You had 16 queues and you're going to carve out a portion of them to do your busy polling. So like you had so many connections that was like, didn't have enough threads to handle all of the work that was hitting them, and how do you deal with that problem because of that type?
So that's a good question. I think there's a couple ways to deal with that. Like, I've thought about this same problem too quite a bit. I think one way you could deal with it is you could write like a more complicated like CBPF or eBPF program to map multiple threads to a single NAPI ID and have each of those do like busy polling on separate CPUs. Although I think there might be some locking problems you would run into. I'm not like 100% clear on that. So I don't know like a good answer to your question, but I have thought about this problem. I haven't had time to like go down the rabbit hole and like research it, but it would be nice. And if it were possible to have multiple threads busy polling same NAPI ID at the same time on separate CPUs, because then you could write like an eBPF program to do that for you. There's one more another question over here.
So you're mapping each hardware queue of each NIC to a separate CPU, whatever, right? So what happens if you have a very unbalanced workload across hardware, across NICs, across queues? Will that end up leaving like CPUs unutilized?
Yeah, it will. Yeah, it will. Yeah.
Is there any way you could have multiple NAPI IDs on the same CPU? Like, is there a way to busy poll multiple at the same time or anything?
So the problem that you're describing is a real problem and is a thing like I'm worried about, which is like one of the concerns with like trying to figure out how to deploy this, like, you know, like more widely. I don't know the answer to that question yet. Like that's like a thing like I'm still trying to figure out like how to get to that point. But at least at first, like the safety mechanism that like you know, I've been thinking about implementing internally is like if we detect that a case like that is happening where there's like significant imbalance or like there's a lot more traffic coming in for NIC. Because that's one of the trade-offs in the design, right? Is like if you're doing the reuse port thing in the vanilla configuration, then any thread can accept a connection coming in on any NIC, and so naturally you have more CPU that can be utilized if, like, let's say NIC 4 gets more traffic. If you know shrink the reuse port groups, be NIC specific, then you're obviously going to lose like some CPU capacity. I think like in that case, like if it's like severely imbalanced, one of the things that I want to do is add a safety mechanism into the app where we can just say like, you know, disable the BPF filter and then just do just connections wherever they're going to go and stop doing busy poll. I don't have a better answer than that right now, but both of you have like really good questions, and like those are like very real concerns that I think like hopefully, you know, we'll be able to address in time.
Question: could you create multiple epoll instances and put different NAPI IDs into each one of them off of the same thread?
I guess,
because
yeah. I
you
guess you
said like
could.
the epoll busy, the polling only works if all of the FDs there.
Right. So you're saying create multiple sets
like,
and call epoll weight multiple times on different
Right.
sets. Yeah, you could do something like that potentially. Yeah. Yeah, I need to think more about that. Sorry, it's hard to like think and also be in front of a huge crowd at the same time. But
Yeah.
that's a good idea. All right, cool. I'm around at the conference. If anybody wants to talk about any of this later, feel free to hit me up. I'll be around. Thanks a lot for listening to me talk, and hope you all have a good conference.